Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Max Planck's 8 lectures on theoretical physics, delivered in 1906 at Columbia University, represent a pivotal moment in the development and dissemination of early quantum theory. These lectures, meticulously transcribed and later published, offer a unique glimpse into the mind of a physicist grappling with revolutionary ideas which, at the time, stood in stark contrast to the well-established edifice of classical physics. To appreciate the significance of these lectures, one must first understand the intellectual climate that preceded them, the specific challenges they addressed, and the profound impact they had on the subsequent trajectory of physics. The late 19th century saw classical physics, particularly Newtonian mechanics and Maxwellian electromagnetism, reach a perceived zenith. Many physicists genuinely believed that the fundamental laws of nature were largely understood, with future work focused primarily on refining existing theories and determining physical constants to ever greater precision. However, a few persistent anomalies stubbornly resisted explanation within this classical framework. Chief among them was the problem of blackbody radiation. Classical theory predicted that the energy radiated by blackbody, an idealized object that absorbs all incident electromagnetic radiation, should increase without bound as the frequency of the radiation increased. This prediction, known as the ultraviolet catastrophe, was in blatant contradiction with experimental observations. Experimental data demonstrated that the blackbody spectrum peaked at a specific frequency, which was dependent on its temperature, then decreased at higher frequencies. Several attempts had already been made to reconcile theory with experiment. Wilhelm Wien had proposed a distribution law that fit the experimental data at high frequencies but failed at low frequencies. Lord Rayleigh and James Jeans derived another distribution law based on classical equipartition theory, which accurately described the low-frequency behavior, yet predicted the aforementioned ultraviolet catastrophe at higher frequencies. It was into this theoretical impasse that Max Planck stepped. In 1900, driven by a desire to reconcile theory with experiment, Planck introduced a radical hypothesis that the energy of electromagnetic radiation is emitted and absorbed not continuously, but in discrete packets, or quanta. The energy of each quantum was proportional to the frequency of the radiation, with a constant of proportionality, h, becoming known as Planck's constant. This was an audacious departure from classical physics, which assumed that energy could take any continuous value. Planck initially viewed this quantization of energy as a mathematical trick, a convenient way to derive a formula that accurately described the blackbody spectrum. He remained skeptical of its physical reality, hoping that eventually it would be possible to derive the same result from classical principles. The 8 lectures provide invaluable insight into Planck's thinking during this critical period. He meticulously outlines the experimental evidence for blackbody radiation, the failures of classical theory, and the steps that led him to his quantum hypothesis. In the lectures, Planck presents his derivation of the blackbody radiation formula, explaining the assumptions and approximations involved. He emphasizes the role of entropy and statistical mechanics in his derivation, highlighting the connection between the energy distribution of the radiation and the number of ways that energy could be distributed among the various oscillators in the blackbody. A key element of Planck's approach, elaborated upon in the lectures, involves the concept of elementary resonators. Planck hypothesized that the blackbody's walls contain a large number of these resonators, each capable of oscillating at a specific frequency. He then calculated the average energy of these resonators using Boltzmann's statistical methods, but only after imposing the condition that the energy could only take on discrete values, integer multiples of h times the frequency. This constraint, seemingly arbitrary at first, proved crucial in obtaining the correct blackbody spectrum. He presents a convincing argument that classical theory, which allows for continuous energy values, inevitably leads to the ultraviolet catastrophe. The lectures also delve into other topics in theoretical physics, including thermodynamics, statistical mechanics, and the theory of electromagnetic radiation. Planck demonstrates his mastery of these subjects, presenting them in a clear and concise manner. These sections, while not directly related to quantum theory, provide valuable context for understanding Planck's overall scientific worldview. It is a testament to his deep understanding of the foundations of physics. The initial reaction to Planck's quantum hypothesis was mixed. Some physicists, particularly those wedded to classical ideas, were deeply skeptical. Others, including Albert Einstein, quickly recognized its profound implications. In 1905, Einstein published a paper in which he extended Planck's quantum hypothesis to explain the photoelectric effect. the emission of electrons from a metal when light shines on it. Einstein proposed that light itself consists of discrete packets of energy, which he called light quanta or photons. This was an even more radical departure from classical physics, which treated light as a continuous wave. Einstein's explanation of the photoelectric effect, for which he later received the Nobel Prize, provided strong evidence for the physical reality of quanta. The 8 lectures had a significant impact on the development of quantum theory. They introduced Planck's ideas to a wider audience, including American physicists who were eager to learn about the latest developments in Europe. The lectures also stimulated further research on quantum phenomena, leading to a rapid expansion of the field. Physicists such as Niels Bohr, Werner Heisenberg, Erwin Schrödinger built upon Planck's and Einstein's work, developing the framework of quantum mechanics that we know. One can find direct applications of the concepts discussed in the lectures. Planck's black-body radiation formula, for example, became an important tool for determining the temperatures of stars and other celestial objects. The quantum theory of specific heats, which was also inspired by Planck's work, helped to explain the behavior of materials at low temperatures. The development of lasers, transistors, and other modern technologies relies heavily on quantum mechanical principles. Planck's work also faced its share of criticism. Some physicists questioned the ad hoc nature of his quantum hypothesis. They wondered why energy should be quantized, and what physical mechanism was responsible for this quantization. Others raised concerns about the apparent contradiction between quantum theory and classical physics. How could light behave as both a wave and a particle? These questions led to intense debates and further research, ultimately leading to the development of more sophisticated quantum theory. The influence of 8 lectures on theoretical physics extends far beyond its immediate impact on the physics community. It serves as a historical record of the birth of quantum theory, offering insights into the intellectual journey of one of the most important physicists of the 20th century. It also played a vital role in shaping the development of quantum mechanics, a theory that has revolutionized our understanding of the universe. Planck's lectures directly influenced many physicists who attended or read the published transcript. Robert Millikan, for instance, was initially skeptical of Einstein's explanation of the photoelectric effect, yet his meticulous experiments ultimately confirmed Einstein's predictions, providing further support for the quantum hypothesis. Niels Bohr, who developed the Bohr model of the atom, drew inspiration from Planck's quantization of energy. In conclusion, Max Planck's 8 lectures on theoretical physics stand as a cornerstone in the history of modern physics, delivered at a time when classical physics was beginning to crumble under the weight of experimental anomalies. These lectures presented a bold and revolutionary idea that energy is quantized. While initially met with skepticism, this idea ultimately transformed our understanding of the universe, laying the foundation for quantum mechanics and paving the way for countless technological innovations. The lectures provide an intimate glimpse into the mind of Planck during this transformative period, revealing his intellectual struggles, his motivations, and his profound insights. They remain a valuable resource for anyone interested in the history and development of quantum theory, a testament to the enduring power of human curiosity and the relentless pursuit of knowledge. It is perhaps a touch ironic that Planck, an individual of conservative scientific temperament, ushered in such a radical revolution, a testament to the power of confronting experimental truth even when it challenges core beliefs.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.